Yes, okay.
Welcome everybody to Shun Watanabe's talk. It's a great pleasure to welcome him. Shun got his undergraduate and graduate degrees, including his PhD from the Tokyo Institute of Technology. And then Shun joined the University of Tokushima as a faculty member. And we had the pleasure of hosting him for 2 years here at the University of Maryland. And now Shun is a faculty member at the Tokyo Institute of Agriculture and Technology. So I mentioned that Shun was here at the University of Maryland. It was a great pleasure for us. And we soon found out that Shun knows everything. So for me personally, it was a wonderful learning experience. Shun is very well versed in a wide range of things, from multi-user information theory, network information theoretic security, quantum information theory, quantum cryptography, and very importantly, fountain pens. So now I hand you over to Shun, who's going to talk to us about common randomness and the identification problem. Welcome, Shun.
Okay, thank you very much for the kind introduction, Prakash. So, okay, so first let me share my screen. Okay, so you can see my screen now?
Yeah, we can see.
Okay. Okay, so today I'd like to talk about, this talk is something about the, identification and common randomness. So these are quite classic topics, so some of you might already know this, but I'm going to explain some basic results on these topics. So there is some reference. So identification problem, today's talk is based on from a bunch of papers, but common randomness part, the one reference is it's kind of advertisement. So this is a recent review paper, communication for generating correlation, a unifying survey. This is a review paper I wrote with Madhusudan and Himanshu Chagi. In this year's IT transaction. Okay. So let me start with what is identification problem. So we have two parties, or P1 and P2, and P1 observes some value A, which is a vector of length m, and P2 observes some vector B, which is a vector of length m, and they want to compute equality function. So this function is 1 if A equal B and 0 if they disagree. Okay, very simple function. And this kind of problem is a well-studied problem in, for instance, this is well-studied function in communication complexity. In theoretical computer science. And why this function is interesting? Mainly because for this function, randomized protocol significantly improve. Okay, maybe on deterministic protocol. So this identification function, equality function, is one of typical example in which randomized protocol significantly improves upon deterministic protocol. And also, this identification problem has been studied in information theory as well. It was studied as identification via noisy channel. By Ahlswede and Dueck in 1989. And the domain size, this domain size is this problem is interesting from information theoretic point of view because the domain size is characterized by Shannon's channel capacity. And in fact, unlike the standard channel coding problem in which we can transmit a message of 2 to the power message of size 2 to the power nc. In identification problem, we can identify doubly exponentially many messages. It's quite surprising. Okay, so I'll explain these things one by one.
Shun, this is Prakash.
Yes.
May I make a comment?
Yes. You can ask a question anytime. Yes.
Just of historical interest, the identification was studied first by, I think, by one of my colleagues here at the University of Maryland, Joseph Jaja, who's a computer scientist.
Jaja, yes.
He's now the department chair. So his work was communicated to Rudi Ahlswede and Gunter Dueck, and they started looking at their version of the problem. So they enlarged the problem and then looked at the information theoretic aspects of it, and the rest, as you know, is, well, we all know.
Yes.
Right. Thank you.
Okay. Yeah. Thank you very much for pointing that out. Yes. Okay. So let me start with some deterministic protocol. So P1, we have P1, P2. And so they can communicate. So for instance, P1 can send some message, compute it from his observation, and send this to P2. So in general, P1 and P2 can communicate interactively, but for simplicity, we consider just one-way communication. This problem is already interesting enough. So based on this message pi, P2 compute the value, so dp of pi, and we require that this output coincide with equality function for every a and b. Okay. So equality function can be written like so in function table, the equality function can be written like this. And if the message for input A1 coincide with the message for input A2, then P2 cannot distinguish A1 and A2. In fact, if the output for the message pi of A1 is coincide with the equality function for b equal A1, then this value must, because pi of A1 coincide with pi of A2, so the output, this output must be also 1, but the equality function for B and A2 and B must be 0. So for A2 and B, the output does not coincide with the function value. So in order to satisfy this condition for every A and B, P1 has to send m bit. M bit must be transmitted. If we only consider deterministic protocol. Okay. Next, let's consider randomized protocol. So in randomized protocol, P1 and P2 share some common randomness U, which is binary sequence of length L. Okay. And so P1's message can depend on this common randomness and send this message to P2. And because P2 also knows the common randomness, his output can depend on the common randomness as well. And also in the randomized protocol, we allow some error. So our requirement is that P2's output this disagreement of P2's output to the function is small for every A and B. So this probability is with respect to common randomness U. Okay, A and B are deterministic. Okay, so let me explain one concrete example of a protocol with common randomness. So, assume that A and B are element of finite field. We use algebraic structure and sample U1 through UK, which takes value of finite field to the power m at random. So P1 and P2 can sample these guys using U. Okay, and P1 sends a message as follows. So he computes the inner product of U1A, U2A, UK, and A. Okay. Okay, so this is message pi1, this is message pi2, and this is message pik. So P1 sends k-bit message to P2. And P2 output 1 if the inner product of Ui and B coincide with pi I for every I between 1 through k. Okay. So this is the protocol. And if A equals to B, in this case, because the inner product of Ui and A must coincide with the inner product of Ui and B for every I. So in this case, P2 can correctly compute the value of equality function. When A and B disagree, in this case, because Ui is sampled from this set at random, so the probability that the inner product of Ui and A coincide with the inner product of Ui and B, this is probability that Ui inner product of Ui A minus B equals 0, which is half. So we have k inner products. So probability that P2 erroneously output the function value is bounded by 1 over 2 to k. So for instance, if we set k equal log 1 over epsilon, the error probability is less than epsilon. Okay. So here, for fixed epsilon, the message length k is constant, does not depend on the domain size m. Okay. But the size of randomness we used is so this each UI is this is n bits. So the size of common randomness we used is m times k. So it is quite large. So next we want to consider more randomness efficient protocol. Okay, so in order to construct randomness efficient protocol, we use some bounding technique from probability theory, very basic bound known as Chernoff bound. So let Z1 through Gn be independent Bernoulli trial with probability being 1 is P. Okay. Then probability that the arithmetic mean of Vi exceed 1 plus delta P is bounded by e to the power delta square P n 3 for any delta. By the way, so expectation is of course this is P. So deviation from the expectation is exponentially small. So we use this basic bound. So let's consider the following table. So V is some value. This is the domain of the function. U is some value. So this U describe some value of common randomness. Okay, and then so we consider arrays of random variables indexed by V and U, like this table. To T of 2 to the power M. Okay. So this T V U is randomly sampled from k-bit set. Okay. Here k is set as this value log 1 over epsilon. Okay. Then for A not equal to B and U is the value of common randomness, by the way. Probability that this indicator function of TAU equal TBU equal 1 is 1 over 2 to the power k. Because when A and B disagree, these random variables are sampled independently. So the collision probability is this, which is epsilon. And also note that this indicator function of when A disagree with B, A and B disagree, random variable T of A1 equal T of B1. T of A2 equal T of B2. T of A2 to the power L equal T of B2 to the power L. These are independent Bernoulli. With probability of 1 being epsilon. So by Chernoff bound, probability that this arithmetic mean exceed 2 to the epsilon is less than e to the power epsilon 2 to the epsilon square 2 to the power L over 3. Okay, so by union bound, oh sorry, not this is epsilon is okay. So sorry, this is epsilon. We apply Chernoff bound for delta equal 1, by the way. So union bound, by union bound, probability that exist A not equal B such that arithmetic mean of these guys exceed 2 epsilon is less than 2 to the power 2m times this guy. Okay, so if this probability is less than 1, then there exists a realization T of VU such that for every A not equal B, collision probability of collision is less than 2 epsilon. Okay, and by solving this this equation, the domain size M must satisfy this formula. So these guys are just constant, and for fixed epsilon, this is also constant. So logarithm of the domain, bit length of the domain must be less than the length of common randomness. Okay, as long as this equation is satisfied, we can find a protocol with error probability 2 epsilon. Okay. So in summary, so there exists identification protocol such that the size of common randomness is L bits, and the communication cost is k equal log of 1 over epsilon. So this is constant for fixed epsilon, and the domain size M is 2 to the power of L minus some negligible term. Okay, this is bits. Okay, so for given L bits common randomness, we can identify exponentially many bits of messages. Okay. Okay. So far, any question? Okay. Can I proceed? Okay, so next, let's consider the case where P1 and P2 share imperfect common randomness. So they share IID observations, xn and yn. And they have, again, they have their input. Okay, and so P1 sends some message. So this time, P1's message is computed from his input A and his private randomness. This U1 is private randomness. And xn, okay? And suppose this is S bits. And then P2 output something. So output is based on his input and the message, and also his random variable yn. And we want to bound the probability that the output disagree with the output of the function. So we want this probability to be smaller than epsilon for every A and B. Okay. So this x and y can be any correlated random variable. Okay. And if exists a protocol satisfying this we say such a protocol is NMS epsilon ID protocol. Okay, and for given communication cost S, we define M epsilon star of S given Xn, Yn. So we define this as primum of the length of the domain such that exists an MS epsilon ID protocol. So for given communication cost, we would like to maximize the length of the domain size. Okay. And in the asymptotic regime, we can define the identification capacity as follows. So for given rate R, R is some rate. So we consider logarithm of this optimal message length for given, so given NR. So the communication cost is NR bits, and this is the length of domain size, and we take logarithm and divide by the block length, and take lim_inf of n, and take limit of epsilon to 0. Okay. So here, note that we take logarithm of message length, so the domain size is doubly exponentially large. Okay, so this is something. Okay, so this is IT formulation. So this is information theoretic formulation. We are interested in characterizing the capacity for given rate. So the communication cost is NR. And the observation, we want to evaluate the growth rate for the length of the observation, okay, in information theory formulation. And similar problem has been studied in computer science as well. So in computer science, they usually consider the case where the observation length is infinite. Here, observation length means the length of xn and yn. Okay, so they usually assume that the length of xn and yn are infinite. So for given communication cost S, we consider this value, take logarithm, and take supremum of n because these are regarded as free resource. And then we are interested in evaluating the growth rate with respect to communication cost. Okay, let's define this quantity as C tilde of ID. And because we can always use the protocol for IT formulation by setting S equal NR. So the asymptotic limit for CS formulation is as large as supremum of the capacity in IT formulation over R and taking supremum over R. Okay. But this can be proved, but this direction is this is not known. Okay, so this is a problem of identification using some correlation. Next, let me explain problem of common randomness generation. This problem was introduced by Ahlswede, Chisar in 1999. So the situation is very similar. We have P1, P2, and they observe X and Yn. And in this problem, there is no input A and B. They only observe X and Yn. And instead of computing equality function, they want to generate common randomness. For that purpose, P1 sends some message, pi, computed from his private randomness and Xn to P2. So this is S bit. Okay, and then P1 generate some random variable U based on his private randomness Xn. And also P2 compute random variable U hat based on his observation Yn and the message pi. And we require that probability that U hat disagree with U is small, epsilon. And the probability, the distribution of U, this U, is close to uniform distribution. So this is variational distance. And P unif is uniform distribution on the L-bit space. Okay, and if there exists a protocol satisfying these conditions, we say that protocol is NLS epsilon delta protocol. And for given S, we define L epsilon delta of S xn yn as the supremum length, such that there exists an LS epsilon delta protocol. So for given communication cost S, we would like to maximize the length of common randomness that can be shared between P1 and P2. Okay. And again, we are interested in the asymptotic limit of these values. So for given rate, we define common randomness capacity as so for given communication cost NR, this is the length of common randomness P1, P can share. And we would like to evaluate the growth rate with respect to the block length of xn by n. Here, note that we don't take logarithm here. Previously, in the identification problem, we took logarithm, but here we don't take logarithm. So the range of common randomness is like this, okay? So this is IT formulation. And also we can consider CS formulation. So in fact, common randomness problem has been studied quite recently in computer science people. For instance, it was studied by Canonical, Sudan in 2015, and there is some follow-up work by Goswami. Krishna. Okay, so in CS formulation, again, as in computer science, they consider xn and yn as the length of xn, yn as infinite. So we consider for given communication cost S, we take supremum of length n, and we are interested in growth rate with respect to the communication cost. Take limit of communication cost, and we take epsilon delta to 0. Okay. So this common randomness problem has been solved in the literature. So in order to characterize this capacity, we need to introduce some function. So for given rate r, we introduce function f of r as maximum of the mutual information between u and x, where this u is some auxiliary random variable satisfying this Markov chain constraint. And the size of this auxiliary random variable can be bounded by the range of x plus 1, and also the conditional mutual information between u and x given y must be less than r. Okay. By using this function fr, the common randomness capacity is known to be fr if r is less than some critical rate, and above the critical rate, it is mutual information between x and y plus r. So what is this critical rate? This critical rate is defined as infimum r such that this function fr coincides with this straight line. So in picture, the shape of this function is typically something like this. We have, this is the mutual information. So we have this straight line. So this critical rate R star is the point where this curve touches this straight line for the first time. And in general, this critical rate is less than the conditional entropy of x given y. This straight line is this one. Any question so far? Can I continue?
Yes, please. Yeah.
Oh, okay. So let me briefly explain how this capacity can be attained. So this point is very easy to understand. So this point, this is in this case. So this is R is conditional entropy of x given y. So this value is h of x. So this point is attained by the Slepian roof coding. So distributed coding. So P1 sends roughly n times h of x given y bits message. so that P2 can recover xn with small error probability. Then by using xn, P1 and P2 can generate roughly n times hx common randomness. Okay, so this point is very easy to attain. This curved point require more involved coding, which is kind of Wawa-native coding in rate distortion. So we have this xn space and yn space, and we need to introduce auxiliary random variable, and by randomly generate some point to quantize this x source in the similar manner as rate distortion problem. So we create roughly 2 to the power n u, the mutual information between u and x points. Okay. Then okay, then so we quantize x source into these number of points, and also we use bin coding, and so P1 sends roughly this much bits, which coincide with this conditional mutual information. And we have to choose the auxiliary variable so that this is less than nr. And then P2 can recover this quantized point. And so P1, P2 can share roughly n times the mutual information between u and x bits CR. Okay, so this is very rough idea of how to attain this rate FR for rate less than critical rate. And the capacity for CS formulation. So in the CS formulation, we are interested in growth rate of common randomness rate with respect to communication cost, and this is characterized as common randomness capacity divided by R. We take sup over this ratio, which is the slope of common randomness capacity at 0. But if common randomness capacity is 0 at rate 0, so this is So the CS formulation is characterized by the slope of this curve at r equals 0. Okay. Next, let me explain the connection between identification and the common randomness problem. So recall that for identification, yes.
Question. This Prakash. Hi.
Yes. Yes.
Both the formulations that you described just now, communication.
What formulation? Sorry.
In both the formulations, the information.
Both the
formulations, communication was one way, right? From the X terminal to the Y terminal.
Yes. Well, one way. Yes.
Now,
but you can also consider interactive one also.
Okay. And how does it matter where you begin, for instance? In other words, is one favored over the other? Is it better to start with X communicating to Y, or vice versa?
In interactive case, you mean?
Interactive case, yes.
In interactive case, for it depends on how many rounds of communication you allow. So if for finite round protocols, who communicate does matter in general, I think. But if the Excuse me?
No. Is it known that it doesn't matter, or is there a question as to whether one direction, starting in one way, improves upon the other?
I don't know. I don't know any explicit example in which P2 starting protocol improves upon P1's starting protocol.
And for instance, is there a condition of the kind, if you look at the two conditional entropies, if one is larger than the other, then it suggests that communication begin in one direction or the other.
Yes. So I think it is not difficult to create some example.
Okay. All right. We can come back to it later.
Okay.
Thank you.
So okay. Any other question so far? Okay. So we would like to consider the connection between identification and common randomness, and recall that for perfect common randomness case, there exists a protocol such that size of CR is L bits, and communication cost is constant, and domain size is exponential. So for imperfect randomness case, for communication cost NR, we can use, first we use NR minus k bits for creating common randomness. So in this step 1, we can create roughly n common randomness capacity bits of CR. And then by using this amount of common randomness, the parties can identify this much bits. Okay, identification. By this two-step protocol, so for given rate, identification capacity is at least as large as common randomness capacity that we can show. But opposite direction, this is not known in general. Okay, this is open question. Okay, so next, let me move to problem of identification via noisy channel. So this is okay, so in this formulation, again, we have two parties and they have inputs, n-bit inputs. And here, instead of noiseless communication, they are connected by a noisy channel, discrete memoryless channel, and uses of discrete memoryless channel. So P1 sends some input signal xn, then P2 receive some output signal yn. So we consider DMC given by stochastic matrix W of y given x. Okay, so when P1 observe his input A, he creates some input signal stochastically. His coding scheme can be described by a stochastic distribution depending on his input PA. So PA is a distribution on the alphabet, product alphabet. Okay. So for given input A, his message is distribution, coding is distribution. So the entire coding scheme is described by a set of distributions. On the other hand, when P2 receive signal yn, and when his input is B, P2 output 1 if yn is included in some decoding region, D of B, which is subset of output alphabet. So decoding scheme can be described by a set of decoding regions. But note that unlike the standard transmission code problem, channel coding problem, this decoding region are not necessarily disjoint in the identification problem. And the requirement of error probability is that for every A equal B, probability that when P1 sends something based on A, the probability that P2 output 1 is at least 1 minus epsilon. And when for every A not equal to B, probability such that when P1 sends A and P2 output 1 is less than epsilon. Okay. So if we can find a coding scheme satisfying this one and this one, we say such a code is N M epsilon ID code. And so we define M epsilon star of Wn as supremum length M such that there exists an M epsilon ID code. Okay, so this is identification via noisy channel formulation. And we define the identification capacity over the channel by taking the limit. So error probability goes to 0 and lim inf of the block length. And so we consider the optimal maximum length of message, taking log and divide by the block length. So again, because we take logarithm, so the domain size is 2 to 2. Okay, so this is the doubly exponential coefficients. Okay. So Ahlswede Dueck 89, and also there is follow-up work by Han and Verdu 91. Okay, so they showed that the identification capacity is given by the Shannon's channel capacity, this familiar quantity. Okay. So how do we prove this? So this achievability part, this direction is not too difficult. So first, use standard channel code to send L equal this amount of these bits of common randomness from P1 to P2. So by using the standard error correction procedure with small error probability, P1 and P2 can share this amount of common randomness. And in the second step, by using this common randomness and sends some constant bits with negligible rate, because P1 and P2 already share this amount of common randomness, they can identify these bits. They can identify these bits of message. So we can show identification capacity is as large as the transmission capacity. And in this identification problem, main difficult part is proving this direction. Okay. Any questions so far? Okay. So we would like to. So next I'd like to explain some proof idea of this converse part. So it is very difficult to prove converse impossibility for arbitrary identification code. So first step of proving converse is restrict ourselves to some class of some special class of codes, identification codes. So which is sometimes called canonical code, canonical ID code. So for an integer m, and for an integer m, a distribution p, okay, on this input alphabet is called m type if probability of each signal is some integer multiple of 1 over m. So it's depending on the signal, we pick some integer. So if distribution P has this form, we call that distribution M type. Okay. And NM epsilon ID code is said to be M canonical if PA is the distribution corresponds to the input A, by the way, okay. If PA is M type for every message, okay. Sorry, let me get some water. Okay, so this is M canonical ID code, definition of M canonical ID code. And first, we saw that for M canonical code, the message length cannot be too large. So we prove lemma, let's say lemma star 1. Okay, for a given M canonical and M epsilon ID code with 2 epsilon larger than 1, smaller than 1, we have okay, so this is rate of ID code. So this rate of ID code must be smaller than log of m over n plus some small terms. Okay. So when n is large, these are negligible. So for M canonical code, the message rate of ID code can be bounded by this quantity. Okay, so okay, so proof of this lemma is not difficult. So we prove that for canonical code, the distribution corresponds to each message must be all distinct. And by assumption, this is M type. So for first, we prove that this is all distinct. So if there exist 2 messages such that their distribution coincide, in that case, this probability so by the first requirement, this is A and this is A, so this probability must be larger than 1 minus epsilon. But this distribution coincides with P of A prime, so we have here, this is different. A and A prime are different. So by the second error requirement, this probability must be smaller than epsilon. So this contradicts this assumption. Okay. So all distributions corresponding to messages must be all distinct. Okay. And then by assumption of the lemma, these distributions are all M type. And the number of M type on this alphabet is bounded by this, because the M type is essentially the function from this set M, 1 through M, to this set. Okay. So the number of M type is bounded by this. Because these are all distinct, 2 to the power M must be smaller than this. And then we taking logarithm, we get okay. So for M canonical ID code, we can fairly easily derive some converse. So for M canonical code, because we can show some converse, for a given general for given nm epsilon ID code, if we can find m canonical nm epsilon plus delta ID code, with some small delta and m being smaller than the capacity plus some term delta, then we can show that the ID capacity is Shannon capacity plus some small term. So next step is to convert any given identification code to m canonical code with sufficiently small m. Okay. To consider this problem, Han and Verdu introduced a problem called channel resolvability. So this is introduced by Han and Verdu. So the problem of channel resolvability is the following. So for arbitrary distribution, given distribution P in the input alphabet, how much size of M is needed to approximate P of W, the output distribution of the channel for this input distribution. So we want to approximate the output distribution corresponding to the input distribution by M type P tilde. So the output distribution of this M type so approximate in the sense that variational distance between this output distribution and the output distribution of M type should be less than delta. Okay. So they introduced this problem called channel resolvability. Okay. Okay. Suppose that this problem can be solved. Okay. Then we can show the following lemma. Lemma star 2. Okay, so if any distribution can be approximated by M type P tilde such that the variational distance is less than delta, then for given n m epsilon ID code, there exists m canonical and m epsilon plus delta ID code. Okay, so proof is not difficult. So by assumption, we can approximate any distribution by M type. So for each distribution corresponding to message A, find M type P tilde A such that the variational distance between PA, the output distribution of PA and output distribution of M type is less than delta. And here we note that the variational distance can be written as some set P. So variational distance can be written like this. So for any set, the probability of B is evaluated for probability distribution P1 can be bounded by the probability of set B evaluated for P2 plus penalty given by the variational distance. So by using this, we for A equal B, probability. So this is P tilde. This is M type. So this is the probability such that P2 makes an error when we use M type P tilde A instead of PA. This probability can be bounded by the error probability of original code plus the penalty by this approximation, which is bounded by epsilon plus delta. And for A not equal B, similarly, the error probability of the error probability when we use M type is bounded by the error probability of the original code plus the penalty by this approximation. So we can construct NM epsilon plus delta ID code by substituting each PA with M type. Okay, and so this is some theorem proved by Han and Verdu. For arbitrary delta for sufficiently large n. If we set the size of integer as 2 to the power slightly larger than the capacity, then for arbitrary input distribution, there exists M-type P tilde such that the approximation error is less than delta. Okay. So by this and the previous two lemmas, we can show that the ID capacity is less than the Shannon's channel capacity. Okay. Any questions so far?
No, it's fine.
So how much can I continue? I spent quite a lot of time already.
It's supposed to end at 10:30 Eastern time. So maybe you can summarize what you wanted to say. Is that okay?
Yeah, that is okay. Yes.
But we have time for questions, maybe.
Yeah, maybe. Yeah. So summarize. Okay. So this identification problem. So the problem of identification problem is closely related to how much common randomness the party can create using their resource. The resource can be their shared correlation or some noisy channel. And the size, the domain size of identification is doubly exponentially large, and the lower bound of the optimal coefficients is lower bounded by the common randomness capacity. And so in general, it's difficult to prove converse, but for identification via noisy channel, by using some clever idea, we can prove converse. Okay, so this is summary of this talk. And any question or comment?
Shun, thank you very much. This was very clear, and you did it very painstakingly. Thank you very much.
Oh, you are welcome.
Well, are there any questions? I have a question going back to the randomness problem. So suppose you have two samples with observations xn and yn that are correlated, and they want to build common randomness, and they can do this interactively using randomized protocols. And there's a total rate of communication allowed, let's say R. And
total rate is R,
R, yes. And the number of rounds is unrestricted. And so the term
compounded?
Unrestricted, yeah, any number of rounds of communication. But the total rate is fixed, R.
Okay.
Communication. What is known about the amount of common randomness that can be generated? So you see, R is fixed. There is some symmetry in the protocol
Mhm.
that there is no particular direction of communication is favored over the other. And number of
Yes.
rounds is unlimited, but the total rate is fixed. I know that some special cases can be resolved, but in general, is anything understood about this problem?
In general, so for some special case, such as binary symmetric distribution,
Yeah.
so difficulty is mainly converse, I think.
Yeah.
So, and for some special types of correlation, we can derive converse using some sophisticated techniques such as hypercontractivity.
Uh-huh.
But so general case, we need to use single letter characterization argument. But if the the number of rounds is unbounded, then the size of auxiliary random variable is also unbounded, right?
Yes, but the rate is fixed still, right? So you can't exceed
Still,
rate plus the joint entropy of X and Y, right? As common randomness. So that at least there's a bound on that.
yeah. So
And of course, if the rate exceeds the sum of the two conditional entropies, then in one round you can get the joint entropy of X and Y at both terminals, right?
yeah, so
If you
even for unbounded case, so this straight line part is easy to prove, I think. But this curved case, part, we can do single letter characterization, but can we prove achievability for that rate? Maybe no.
just a question.
So okay, so the answer to your question for general case, as long as I know, it is not known for unbounded number of round case.
Okay. So what happens when you bound, when you have the number around, there's one auxiliary random variable per communication, right? That builds up. And so the question is, if you allow for unlimited, in other words, can you control the number of the growth of the auxiliary random variables? That becomes the hard part, because you have these auxiliary random variables and then you have the Markov chains at every step. And then it's keep track of what exactly is going on. So
yeah, but as long as it is finite round, we can bound, and then we can prove corresponding achievability. Yeah, so for finite round, common randomness capacity for given total rate, it has been solved.
I see. And does it give an indication as to where you begin, or you compare the two and say the maximum of the two? In other words, who begins communicating?
Who begins communicate?
So that's also a free. That's also free as a choice.
Yes, but in the case of finite rounds, who start communication does matter in general, right? Okay, yeah, we have to create some example, but I think some example can be created, I guess.
Okay. Very good. Thank you very much. Are there more questions?
Yeah. Can you hear me?
Oh, hi, Sergio.
Hi, Shun. I don't know whether you can see me.
Yeah, I can see you.
Oh, okay.
We can see you.
I would like to also congratulate you, as Prakash said, for a very nice and clear presentation. And also I would like to congratulate Prakash and his colleagues for organizing this very nice Zoom series. So Shun, just a comment. I noticed that, okay, sorry, my phone. So I noticed that you drew these parallels with the computer science literature, especially at the beginning. And I also noticed that in the announcement for your seminar, there was a citation to a recent paper, which I think one of the authors, one of the authors is Sudan, no?
Yeah. It's joint review paper.
Yeah, so these parallels you discuss in that paper, I guess, right?
No, that paper.
Yes.
Yeah. So it's interesting that there seems to be a lag of a number of years, maybe 2 decades or something like that in this particular case, from the information theory literature to the theoretical computer science literature. So I wanted to ask you if in the computer science literature, have you seen anything resembling resolvability, or have they used resolvability for anything? The approximation theory of output statistics?
I don't know. I have never seen channel resolvability.
Okay.
Yeah.
There is something called the reverse Shannon theorem. There is a paper by Peter Shore and Bennett and some other folks more in the quantum, but I think they formulated that also classically. And it looked awfully similar to me to resolvability. So,
yeah. Proving reverse Shannon theorem, we usually use channel resolvability as a building block.
Okay.
Yes.
Okay. Okay. But it has some other ingredients.
It has, it has some ingredient, but I would say main ingredient is channel resolvability.
Okay. Okay.
And also, yeah.
Okay. Thank you so much. And are you in Japan now?
Yes, I'm now in Japan.
Okay. Give my regards to Taesun Han.
Oh, okay. Yeah, sure.
Thank you.
Well, thank you again, Shun. You also see why it was so much fun to have Shun at the University of Maryland for 2 years. So those were 2 very rich years in exploring different ideas for us. So thank you again, Shun, and thank you for a very clear talk.
Thank you very much for organizing this seminar.
Be safe and be well. Thank you all.
Thank you.
And by the way, we also have a good program for the next semester in the seminar series. So this has been one of the silver linings of the pandemic, that we can reach a broader viewership and have more people give exciting seminars. So thank you to everybody.
And also the YouTube channel, so the recordings are and will be available.
Available on YouTube. So we are recording everything and they'll all be available. Thank you all very much. Bye. Thank you, Shun.
Okay, thank you.
Thank you.
Okay,
Bye.
thank you. Thank you, Prakash. Thank you, Sasha.